Welcome back on the main stage. We're starting with our tech track now, so we have a bit more technical speakers coming up now. The first one I'd like to present to you is Nick Sullivan from Cloudflare. Nick Sullivan is going to talk about new developments around the web and how they're affecting security. HTTP and the web technology used to be a simple request-response technique, but this is much preceded now with HTTP 2, which is fairly more complicated. TLS 1.3 just came out a couple of months ago, finally came out. And the whole business of delivering web content is more and more in the hand of the big cloud providers. And of course, the content delivery networks. And one of the biggest ones around is Cloudflare. And Cloudflare is one of the drivers behind this innovation. And one of the people steering that car, so to say, is Nick Sullivan, the head of crypto from Cloudflare. Please welcome Nick.
Test. Okay, all right, it's on. Hello, everybody. Thanks for coming. Thanks for having me. It's great to be here. Today I'm going to talk about the web. First, just a little bit of background on myself. I work at a company called Cloudflare, and I'm trying to help build a better internet for everyone. I've worked on different cryptographic projects in the past. I consider myself an applied cryptographer. And more recently, I've been working on internet standards, specifically TLS 1.3. So in this talk, when I talk about the web, I'm not talking about front-end technologies like HTML or JavaScript or even back-end technologies like Ruby on Rails or Docker or things like that. Instead, I'm going to focus on the underlying infrastructure and protocols that make web services go. And the web is just one of many applications that makes use of the hundreds of thousands of networks that are connected together to make up the internet. And when thinking about building a system like the web, where everybody in the world is trying to access content and interact with it, there's several competing goals. Security is one of them, but two of the ones that people are focusing on a lot lately are privacy and performance. So privacy is a high-level goal. You would agree that, most people would agree that using the web, what you see and what you browse should not be visible to every single third party on the entire internet. And another high-level goal is performance. If you're going to be browsing websites, accessing web services, they should be snappy, they should be fast. And so historically, there's been a tension between this latency aspect, making things fast, and making things private and secure. You can have networks like Tor, the anonymity network, can give you really, really strong anonymity privacy guarantees, but at the cost of massive, massive performance hits. And on the other hand, you can have cacheable plain text protocols that can be very, very, very fast, but yet have almost no privacy properties at all. So in this talk, I'm going to explore a confluence of events that has changed the way that the architecture of the web is built in a way that it makes it possible to actually improve both privacy and performance simultaneously, with some interesting effects on both, as well as security. So these are two classic fundamental protocols that make up the web. This may seem boring. They may seem the HTTP has been around for almost 30 years now, and DNS even longer. But let's explore a little bit of what they are right now, or what they originally were. So the HTTP protocol is what takes web addresses and returns web content. It's a two-party protocol between the client and the server. It's unencrypted. And so your ISP or whatever hop along the path that's actually closest to you can cache content and provide it really quickly. DNS is one of the oldest protocols on the internet. It is as well unencrypted, highly cacheable. It's a query-oriented protocol. People consider it something like the phone book of the internet. It takes domain names, provides IP addresses. So generally, DNS and HTTP, as described, are not very privacy friendly. So let's try to visualize the early web. Because residential networks don't let you host your own content, people tend to use shared hosting providers, and these hosting providers are these dots here. And they are typically, one website is on one computer, one server around the world. And so to access it, you have to often cross national boundaries. You have to make requests all the way across the world. So this can result in some pretty poor performance. And if you have something like a BGP hijack leak, you have no guarantee as to which networks this information is progressing across. Yep. Just going to have a slight adjustment. Okay, and so this kind of shows what the network observer sees. They see everything, really. They see your client IP, which is unique to you, server IP, unique to them, the server URL, well, what site you're going to, and actually the content. So from an anonymity perspective, a privacy perspective, this is pretty much as bad as you can get. And as an aside, one of the reasons I said you have one client IP address, this isn't necessarily true. There's only 4 billion or so IPv4 addresses, and this is not enough for every user and eventually every IoT device out there. So one way that you could imagine this going is using a central node. And this is something you could imagine as a VPN or even a carrier-grade NAT or a network like Tor. And in this situation, if the network observer is between the central point and the web servers, then you get a little bit of anonymity mixed in. So at the cost of, say, 3 round-world trips, potentially, one with a VPN, one with Tor, and carrier-grade NAT, something small. So you can actually twist this around a bit and have some slight anonymity. The identifying one person from another is slightly more difficult. But this isn't where the interesting innovation is happening. Let's talk about some new trends. This has been 20 years coming, but 2 of the major evolutions on the web are involved with shared hosting and encryption. So HTTPS, what is this? This is encrypted HTTP, right? This is a huge upgrade for privacy. The content of everything you visit over HTTPS is encrypted, but it doesn't close all these privacy loopholes. It also is potentially harmful to latency, since connections require more round trips to set up, and you no longer have the caching that you had with clear text protocol. So let's take a look right here. This is HTTPS. TLS 1.2, that's the protocol, the encryption protocol typically used in these connections. It requires 2 full round trips from the client to the server. And as you can see here, it's bypassing the ISP. There's no caching that can go on. So this can end up hurting latency quite a bit. And another thing in TLS 1.2 is the certificate itself. Every website needs a certificate to prove ownership of the domain. That is sent in the clear. So if someone's listening to this connection, they can see what certificate you're connecting to. So TLS 1.3, which was just ratified as an RFC just several months ago, improves the situation somewhat. It reduces the latency by reducing 1 round trip, and certificates are encrypted. So no longer are certificates on the wire something that a third party can track. And you also get some extra properties like forward secrecy. Now this has sort of caused some consternation and some issues with respect to inspection and actually being able to see what's inside of these TLS connections. The forward secrecy is a property that is not very friendly to having a system inside, say, a network, an enterprise network, to be able to look inside of this. So there is a little bit of a tension there. So if you step out for a second and look back, what can the network observer see in this case? You don't see the server URL, you don't see the website content, you see 1 client IP, 1 server IP. But as I mentioned before, this is actually not enough for every website either. And IPv6 is still very slowly coming along. In reality, this doesn't really work. Servers need to present a certificate for HTTPS to work, and for the server to know which certificate to use, it needs the host name. And this is sent in the clear. And this is if you kind of look at how the internet evolved from the sort of early days to this somewhat centralized and diverse environment, you end up with something like this, where it's a little bit more dense, there's more encrypted lines, and there are large hosting providers that end up providing services for quite a few different sites. And in order to save IP addresses, there's a feature called SNI, which is, this enables these shared hosting providers to provide services to thousands or millions of websites without having to use thousands or millions of IP addresses. This has been popular. This is since 2014. It's been growing, and it's now almost ubiquitous. Almost every request has SNI. SNI is essentially just the host name that they're trying to connect to in plain text. So this kind of counteracts some of the effects of encrypting the certificate. Every request that goes to one of these shared hosts has the host name in it. So you know the client IP, you know the server IP, you know the host name. This is not very great for privacy. So this is sort of the situation as it was several years ago. More recently, there's been even more changes to the way these web services work. These changes include more HTTPS and the advent of a low-cost edge services. Well, what is an edge service? Well, this is essentially a third-party service that can serve the website's content close to people. So traditionally, you call this a content delivery network, but it also is authorized to do HTTPS connections. So this reduces latency, provides protection against DDoS, and uses a technique oftentimes called Anycast, which reduces the number of IPs needed. You don't need to have a different IP in every location around the world. You can advertise the same IP address. And this takes the where the web was at several years ago to something that looks more like this. So there's very few long lines. Not every website uses an edge service, so there are fewer of these long lines. But so latency is going to be a lot lower. So you can actually regain some of the performance losses that you had. And if you look at HTTPS, having an edge service actually just brings it closer to the user. So this reduces the cost of establishing secure connections. So this is going to be faster, and it's going to be shorter. So moving this connection where users are actually accessing web content to close to where they are has other potential impacts. It's better for latency, but can we, say, improve privacy and latency together? This is where some interesting changes have been happening to HTTP. Well, first, you can't keep everything hidden online. With edge services that span many domains, maybe there's potentially a way that you can hide in the crowd. Now, here's the kind of technical dive that we're going into right now. This is HTTP 1.1. This is what almost everything was using on the web 5 to 10 years ago. Say you want to go to two websites, burrito.com and beans.com. First of all, you make a DNS query to burrito.com. Then you make a TLS connection on the top to burrito.com. And what you see here in clear is sort of what is visible on the wire, what a third party can see. So there's a burrito.com, it has a certificate, beans.com, it has a certificate. They're both the same edge provider. So observing this, you can see that someone's going to both burrito and beans by looking at DNS, looking at HTTP. Now, HTTP 2 is a new technology that's evolved from a protocol developed at Google called Speedy. And HTTP 2 has a really nice property in that it allows you to multiplex connections together, or multiplex requests over the same encrypted connection. So it also has a not very well-known property called connection coalescing, which essentially says that if both sites that you're going to, burrito.com and beans.com, have the same IP address, and that the certificate up here that of the site that you're visiting contains both names, then you don't need to do two TLS connections. You can just use whatever the first connection is. So you connect to burrito.com, and then can just actually request beans.com. So there's no SNI for beans.com on the wire. It all goes through the existing connection, and this is really good for latency. Well, More recently, this has just been standardized at the IETF, is something called the origin frame. This is a new feature in HTTP 2 that lets the server say, hey, client, I also have beans.com. Just don't even bother looking it up in DNS. Trust me, it's on my certificate. You can just connect this way. And this provides a pretty interesting property because it reduces the number of DNS queries you have to do, so it helps speed things up. And you already have a live connection, so you can go to beans.com and burrito.com together. And if you look at what the attacker can see or what an adversary on the wire can see, you actually don't see beans.com at all. So this is kind of an interesting way to look at this. They can see the client IP, the server IP, and then the first host name. And if you have a lot of host names on a certificate, this is the first time that you can actually increase this anonymity set from the server side. So someone observing this knows that you're going to see one of the sites on the certificate, but they don't know which one. Can we take this further? Well, there's a new proposal in HTTP 2 called certificate frame, which is something that goes along with origin frame. It allows you to prove ownership of additional certificates inside of an existing connection. So if you remember with connection coalescing, the certificate needed to have burrito.com and beans.com on the same actual certificate. This way, the server can opportunistically assert ownership over beans.com. And this, from the side, it actually looks just like burrito.com is being accessed. So you're hiding the beans inside the burrito, if you will. What does this change? This sounds sort of radical, right? This is not what you would expect if you're looking at network traffic to see, okay, somebody's actually visiting two sites, but it only looks like one on the wire. So there's a couple interesting things that happen here. Well, DNS is no longer required. So having a certificate gives you routing authority. Now, in different circumstances, this enables attackers, if they manage to compromise a certificate, they no longer have to actually direct you to a specific site to be able to compromise or to impersonate the site. They can have you connect to any site and then present, say, google.com certificate in a certificate frame and hijack sites that way. So this is a potential risk. And this is something that's being discussed pretty actively right now at the IETF. So in any case, if you look back at the anonymity set case, you have server IP and first host name. And if, as a server, you can predict what the next host names you're going to go to, then you can keep sending certificate frames and origin frames, and it'll just simply look like one connection. So this is all well and good. This is kind of an interesting evolution. It's better for latency. It's better for privacy. There's some security considerations to keep in mind. And when you're talking about HTTP, you often forget that DNS is still clear text, and DNS still leaks everything that you go to over the wire. So new technology, this has just also been standardized, is called DOE, or DNS over HTTPS, which this is one of those unfortunate names, but but it is a really interesting technology, and it's something that people are going to have to pay attention to. So like other protocols like DNS Curve and DNS over TLS, DOE is an encryption scheme for DNS. It's not like DNSSEC, which is a new set of records that are digital signatures. It's actually just doing DNS over an encrypted tunnel, kind of like HTTPS. And yes, DNS over HTTPS. And replacing regular DNS with DNS over HTTPS, actually, it closes some of these privacy holes. There's no longer, people are able to spoof DNS. They're no longer able to see which DNS resolutions you're making for that very first one, say if you're using the certificate frame. And DNS over HTTPS is HTTP 2. It allows you, uses the HTTP 2 to be able to actually have multiplexing of these queries. And yeah, so it's possible to do DNS over HTTPS and have a DNS resolver that provides encrypted responses. And what is the impact of that on latency? Well, if you're using DNS from your ISP, it might actually be closer to the user, so it might be faster, lower latency. Oftentimes, there are different caching levels, different capabilities on different ISPs. With DNS over HTTPS, if there's a large enough edge network providing this DNS, then you can actually get comparable performance characteristics. All right, so let's wrap this all up. Let's tie it all together. So HTTP2 with origin cert and DNS over HTTPS kind of looks like this. You see burrito.com, you see resolver.com. What is the one last thing? How can we get rid of burrito.com? Well, SNI encryption. This is another new proposal. You can simply send a key with your DNS query. DNS over HTTPS makes it more reliable to send keys over DNS. And then you simply send the certificate for beans.com. And on the wire, it looks like this. It looks like an encrypted burrito.com. It's very, very hard to go back from encrypted burrito.com. So it looks like you're just connecting to a DNS server and then to some site that is managed by that site, by that provider. And if you look here again, this is the anonymity set is the set of domains that can be served by the IP. So if you can serve 1 million different domains, if your edge service provider has a lot of different customers, then this is your anonymity set. You can hide your traffic among that. Taking this to its very, very logical final conclusion is what happens is if your DNS over HTTPS provider is also the edge provider for content. Well, in that case, you can make a DNS query. The DNS resolver can say, I know how to serve HTTP for this. DNS over HTTPS is just HTTP2, and it can send an origin frame, it can send a certificate frame, and you can end up getting beans.com without ever seeing anything on the wire except for a connection to the DNS resolver. So, where are these technologies now? Origin, this is standardized. Firefox actually has implemented it for over a year. Certificate is being developed and put into different types of browsers right now. DNS over HTTPS, supported by Google DNS 1111. Also, Firefox has the option, and encrypted SNI is in the latest Firefox. So I've gone a little bit over. I apologize. But there are a couple open questions here, and these are really things that we should consider as an industry when faced with actually changing the fundamental protocols of something as pervasive as the web. And first is, how much privacy does this actually give? We're encrypting more things. Is it actually more private? Website fingerprinting, is that a real thing? What sort of risks? What is the threat model? Another question here is, does a lot of these technologies, they really favor large service providers that have a plethora of different customers. And so does having faster connections and better security and better privacy, does it actually incentivize more consolidation around the big providers? And that's an important question to consider. And then the last one, which is nuanced, but it's come up in a lot of different arenas, is does this performance and privacy gain, are these two factors actually outweigh the legitimate need for external visibility? And that can be talk about in the enterprise, or you can talk about in different countries, national governments, or any other scenario like this, where your IT department or someone else needs to see it. And so I don't know the answer to these questions, but I think they're important things to consider when thinking about this new evolution to how the web is built. And that's it for me. Thank you.
Thank you very much, Nick. We have time for questions. The light is extremely strong here. We have a question. We have Rafael Reichuk. And the first question.
Thanks, Nick, for this amazing talk and for bringing us up to speed with the latest developments. As good as this is for privacy, I think there's one big fundamental assumption, which is you have to put the content on the edge, meaning all the decryption keys have to be aggregated at various points in the network, right? this is fundamentally different than having the system where you have like one network provider or one system that serves the content, right? So keys are essentially aggregated and they are spread all over the world. And I'm talking about the private keys, right, that are used for decryption. So isn't there a big, big risk? I mean, not for privacy, not in the first place for privacy, but later on. What's your comment on this?
Yeah, so that's a good point. When you're talking about reducing the length, the latency of connecting to a service that's providing TLS, they need to have access to the private key. And they may not have to actually, as you suggested, the keys may not have to actually be distributed globally. Another effort I'm working at the IETF is a proposal called delegated credentials, which allows you to keep your certificates in a long-term, more secure location, say in a HSM, or not even share it with your third-party provider. And that still lets them, using short-lived credentials, terminate the TLS connection for as long as you authorize them. So this is a risk, and this is another example of how the understanding of this architecture is going to be changing in the next couple of years.
Okay, thank you.
There's another question over here.
So, I mean, the risk for centralizing is not only with private keys, but also, if I remember correctly, Cloudflare had an incident where they leaked data last year, right? So with all these centralizing at the edge servers, the risk for such incidents also increases, right? So what's your comment on that?
I think, the question's about centralization and what are the risks of this. And I think there are many different aspects of centralization that it can increase risk, such as using shared technology, whether it's a shared piece of software. So when Heartbleed happened, everybody was using OpenSSL, and that was sort of a shared risk distributed among all people choosing to use the same piece of software. I consider the risks of using a certain cloud provider or a certain network provider as similar in that it's all the different customers that are relying on the same piece of infrastructure. If there's one bug or if there's one security vulnerability, the risk is distributed amongst them all. So I would consider diversity to be an important thing to consider when you're looking at risk inside your organization.
Thank you.
Thank you very much, Nick. As we're in Switzerland, we have chocolate, of course.
Oh, thank you.
Most welcome.